Here, we would like to talk about the thinking skill known as creating a model. This is also known as creating a metaphor. It's also known as making a connection. So a metaphor states that something, let's call it the concept, is something else. Call it the model. So we can say that the concept has a model or that there's a connection between the concept and the model. To have a successful model, we need to answer the following questions. Is the model less complicated to understand than the concept? So you want to model your model to be, in some sense, easier to comprehend than the concept itself. The next question is, are there many properties of the concept that have counterparts in the model? So if you can accomplish that, the more the merrier. And also you have to understand at one point does the model break down, that the model doesn't work anymore. As usual, we take an example from real life only the first time we introduce the idea, and the example has to be suited to the audience. So here I can talk about marriage is a partnership, and here partnership is a model for the marriage. The husband and wife play the roles of partners. Happiness in marriage is similar to wealth in a partnership. Benefits similar to profits. Sharing responsibility similar to sharing work. And children somewhat similar to employees. Of course, this model will not work for everything. For example, in partnership, there's no counterpart for love, and one would hope that in marriage there is some love. There's other examples. We are full of other examples. For example, another example would be to say life is a journey. Another example would be to say that the stock market is a bubble, or that Bob is a loose cannon. We also have lots of metaphors in using a computer. For example, the first screen that you see on your computer when you log on is called the desktop. And of course, the top of your desk is a model for that idea of the first screen. Or similarly, the pointing device that you used called the mouse. Very early, the first lesson in Math 1 is creating a model. And we talk about the number line, and the number line is introduced as a model of real numbers. We talk about 0 as being the start of the number line. We put the positive numbers on the right side. So the right side of the number line is for positive numbers, left side is for negative numbers. Adding numbers with the same sign is moving in the same direction, be it left or right. Adding numbers with opposite directions is moving in one direction and then reversing direction. So this model is a beautiful one. In fact, it's so good that it's very hard to see at what point the model breaks down. Another model is for modeling fractions. Now, in most textbooks, fractions are introduced using what I call the pizza model. Okay, so 3/4 means take a pizza, divide it into 4 pieces, and take 3 of the pieces. That's a model of the fraction 3/4. This model is not very good because it breaks down very quickly. For example, if the numerator is larger, that is, if we have an improper fraction, there's no counterpart in the model for it. There's also no counterpart in the model for negative fractions. There's another problem also. It makes perfect sense to add to a plate that contains 1/3 of a pizza half another pizza. So In the model, you have 1/2 plus 1/3, but there's no clear indication of how does that relate to the full pizza. So because of that, those reasons, I prefer the number line model of a fraction. So I want to argue that this is a much more superior model of the number line. So I'll go over this very quickly. To model -5/3, we take the original number line, divide each section into 3 more sections, and then use the numerator as steps, just as before in this new number line. So every fraction will have a new number line associated with it. Now, this illustrates also that the model goes a long way. For example, when we compare two fractions and one denominator is a divisor of the other one, like 2 is a divisor of 6 here, what does that entail about the corresponding number lines? Well, it means that the number line for divide by 2 is contained in the number line divide by 6, and building up fraction is just going from one number line to another one. So 5/2 has a counterpart, has a place exactly on the divide by 6 number line, and how many steps do you have to go there to reach it? With this model, you can understand reducing fractions also very well, because reducing fractions means that you go from a number line that has more subdivisions to a number line with less subdivisions, as shown in the figure. Adding fractions, then it becomes clear that you have to consider 3 cases. The case of the same denominator means that both fractions reside on the same number line. So the addition is just the adding of the steps. So this is a very easy case, and why it should be that way. Case 2 is when one number line is contained in another number line. That is, one denominator divides the other one. In this case, the LCD is the bigger number, and so all you need to do is to change one of the fractions. In other words, put the point on the fraction with the smaller denominator on the other one. In other words, this is the building up case. Now, once you do this, both fractions will be on the same number line, and you're reduced to case 3, and finally reduced to case 1, I'm sorry. And finally, in case 3, we have two number lines that do not have this property, namely one is not contained in the other, and vice versa. So here's where you have to go to a third number line called the LCD, which contains both of them. And that shows that this model is very powerful, and it helps explain fractions a lot better than the pizza model. I hope this illustrates the idea of creating a model and its usefulness for the students.